let us talk a bit about Riemann sums in general, and we could have what are called left Riemann sums, right Riemann sums, and midpoint Riemann sums. And each of these distinctions really have to do with where the height of our rectangles is calculated. So, for example, we'll stay with our function f of x equals x squared plus 1, and we'll deal with the interval from 0 to 2 to keep it simple. And we're going to say that n equals 4, where this is the number of subintervals or rectangles that we will create. So graphically, the scenario looks something like this. X squared plus 1 has a vertex at 0, 1, and increases to the right. When x is 2, y is 5. When x is 1, y is 2. Now, a left Riemann sum of 4 rectangles means that we're going to have rectangles that are half of a unit wide, and that the height of the rectangles will be calculated at the left-hand side. So here is one rectangle, here is a second one, here is a third one, and here is the fourth one. Right, so here's our 4 rectangles. And because our function is increasing on this entire interval, a left Riemann sum ends up being an underestimate, because the left-hand side is always lower on the low end of the curve, so to speak. Right? An approximation of the area would be 1/2, that's the length, or the width of each rectangle, times the height at each point. So when x is 0, y is 1, so that's the height of our first rectangle. When x is 1/2, y is 5/4, so that's the height of our second rectangle. When x is 1, y is 2, so that's the height of our third rectangle. When x is 3/2, we are at 9/4 plus 1, 13/4 is the height of our fourth rectangle. So a left Riemann sum for the area of this curve, the sum equals, or the approximation would equal 30/8, or if we reduce that down, it is 15/4. Now, we could do the same thing, but this time we're going to do a right Riemann sum. And this means that it'll be at the right-hand side where each of our rectangles is touching the curve. So this means our first rectangle, the height is found at 1/2. Our second rectangle, the height is found at 1. For our third rectangle, the height is found at 3/2. For our fourth rectangle, it's at 2. And clearly you can see this will be an overestimate. Right? And in all cases, when the function is increasing over the entire interval, then the right Riemann sum would be an overestimate. In this case, the calculation for the approximation is half of the area times, well, we know the area at 1/2 is 5/4. At 1 it's 2. The height at 3/2 is 13/4. The height at 2 is 5. So the approximation for the area as a right Riemann sum would be 46/8, and that reduces down to 23/4. Now we could do this another way. As an approximation, we could do what's called a midpoint Riemann sum. And this means that the height of each rectangle is calculated at the midpoint. So instead of the left or the right, right in the middle. And that would look like this. We would be having rectangles in the middle of each interval. So in this case, it would be at 1/4, and at 3/4, and at 5/4, and at 7/4. And our rectangles would look roughly something like this. And so you can see that you've got a little bit of overestimate, in this case on the left-hand side of each rectangle, but then a little bit of underestimate on the right-hand side of each rectangle. And you'd think in this case it might even be more accurate to the actual answer. So in this case the calculation would be, well, each rectangle is only a half. So the height at 1/4 is 17/16, at 3/4 is 25/16, at 5/4 is 41/16, and at, what would that be, 7/4 would be 65/16. And when we combine all of those things and multiply by a half, we would get 148/32, which simplifies down to, what's this going to be, 37/8. So we have three different approximations for the same area. And each of these are Riemann sums, which are just approximations of area under curve using rectangles whose heights are calculated at a specific point. Now, what we're going to learn how to do moving forward is how to actually find the actual answer. And to do that, we would need to look at what's called the definite integral from 0 to 2 of x squared plus 1 dx, where x squared plus 1 represents the height of each rectangle, dx equals the width of each rectangle. It's gotten infinitely small because we've looked at the limit as n goes to infinity, right? The number of rectangles has become infinite of the sum of, as n goes from 0 to, as k goes from 1 to n of our function, so in this case x squared plus 1 times the change in x. This is getting really small as the number n increases, right? Because we're dividing a finite length into smaller and smaller sections. That sum is what this integral is. And just so you know, it ends up being exactly 4 2/3 units. So our estimates are pretty good.